So, how many of you are in a company that has data on mainframe computers? Good. So I'm afraid I might scare the other ones. Anyway, so I work for a French bank that's called Mutuel Arkea. We're an autonomous regional bank. We're part of a national cooperative group that's called Mutuel. We have roughly 9,000 employees and 3 million customers and a balance sheet of 79 billion euros. We are a regional bank with a national network, so I'm actually located on the west part of France, closest to Wall Street and closest to the Silicon Valley, so we have good influence. People in Paris can say that. We're operating in various sectors, so corporate and public sector, consumer finance, online brokerage and banking, private banking, asset management, life insurance, property and insurance, securities and banking services, and payment services. So why Hadoop? Well, first reason is that we have an ever-increasing volume of data to manage. And we do that in a very regulated sector. So I don't know if you've heard of Basel II and Basel III regulations or Solvency II for insurance. But basically, those are rules about the banking sector that we have to comply with. And if we don't, then we can no longer be a bank. So that's pretty bad for us. So we need to produce some compliance reports at specific times. And for that, we need to analyze lots of data. We're also in a very competitive sector, so we need to create value to differentiate ourselves from our competitors. And one of the sources of value that we've identified is the data. So being able to analyze data and create meaningful insights from that data is very important for our operations. We also need to keep costs under control. We're very fond of open source. We've been using Linux in production for more than 10 years. We use Tomcat in production for more than 10 years. We have lots of open source. And as engineers, we like big challenges. So, what challenge? Well, our challenge is very easily to identify in the company. It's black, it's about that tall, it's very expensive, and it's sold by IBM. And it holds most of our business data. So it's the mainframe. So for all of you folks who have never seen a mainframe, that's a mainframe computer. It doesn't have the disks there, it's just the computer. So think about that like your desktop computer. It's just a little bit bigger, a little bit more expensive. So the first challenge is storing data. On the mainframe side, you have basically 3 types of data you can store. What we call VSAM files, so they're virtual storage access method. They're record-oriented files with fixed or variable length records, and they're indexed. We also have sequential files, which are almost like VSAM except they're not indexed. And we have traditional database, IBM DB2 for the mainframe. So that's the 3 kinds of media support we have on the mainframe. What kind of data is stored in those files? Well, most of it, I'd say 99.999% of the data we store is COBOL records, or what we call COBOL records. They're binary data that conform to a COBOL copybook. So a COBOL copybook is like a description of the fields that you have in the record. So it tells you at this offset, it's a string, it's on 5 characters, and the name you're going to use in your COBOL program is blah, blah, blah. So that's the main type of records we have. And we also have what we call DB2 unload records. So we take the relational database, the DB2 database, and we unload it into a sequential files. And each record is basically a binary record that has all the column values stacked together. So On the Hadoop side, we also store some data. It's a little bit more diverse. We have tab, comma, whatever separated values. So those are basically records that fit on one line with different columns that have the separator between them, either tab, column, whatever. We also have text-oriented files like log files. And we have Hadoop sequence files. So Hadoop sequence files is the format we'd like to have for most of our data on the Hadoop side. What we have in our Hadoop sequence file is mostly bytes writable key and values. So we don't do fancy things on the sequence file. We just take row stacks of bytes, put that on as the key, and row stacks of bytes, put that as the value. And that's what we're storing on the HDFS cluster. Those sequence files are block compressed, most of them are. And the bytes writable values contain lots of different things, but you can find types of data that we also have on the mainframe side, mainly COBOL records, DB2 unloaded records, and thrift structures. Well, we don't find thrift structures on the mainframe, but we have quite a lot of those on HDFS. For compression, we use the default codec, and we'll see why a little bit later. So that's for storing data. Now, on to moving data, because the main purpose of Hadoop and the reason why we're operating Hadoop jointly with the mainframe is so we can analyze data that's sitting on the mainframe on Hadoop. So to do that, we need to move the data from the mainframe to Hadoop, and maybe sometimes from Hadoop to the mainframe. So our standard data transfer process is the following. I'm sure if you operate a mainframe, you recognize, and you're operating the same way. We take VSAM files or a DB2 database, and we produce sequential files from that. So IBM provides you, it's included in the mainframe price, a utility that's called IDCAMS, and has a command that's called IDCAMS repro. So you can convert a VSAM file into a sequential file. So basically you're taking all the records, but you're just changing the structure on disk. So you're creating a sequential file, and for DB2 you're unloading whatever table you want to work with into another sequential file. Once you have that sequential file sitting on the mainframe, you transfer, or at least we do, we transfer it on the Unix side. And for that we use one of two tools. We use one tool that's called cross-file transfer if the file is less than 2 gigabytes, and we use FTP if the file is bigger than 2 gigabytes. Because that's the legacy. We have tools that cannot handle data more than 2 gigabytes long. So, 32 bits is a lot for that time. When you transfer it on the first Unix machine, after that you put the data to its final destination using SCP over an SSH connection. The things that happen to the data while you transfer it is on-the-fly charset conversion usually, because on the mainframe you're not using ASCII or UTF-8, you're using EBCDIC. And so we're usually doing charset conversion on the FTP transfer. And one of the bad things is that if you have a sequential file that has variable length records, then we're going to lose the notion of records, because what you're going to get on the Unix side once you've done your FTP is just a bunch of bytes, but you don't know where the record boundaries are. If you have fixed length records, then it's fine. You can say the first case, the first record, second case, second one, etc., etc. So that's the transfer process we have. So it's 1, 2, 3 steps. 3 steps to get the data from the mainframe to the target Unix machine where you can actually do something with it. When we set up a Hadoop cluster, we design a transfer mechanism so we can move the data from the mainframe to the Hadoop cluster in a more efficient way than what we were doing previously. So what we do is We're able to handle natively VSAM or sequential files. So if your data is lying in DB2, you still have to do the nload to create a sequential file. But if you have either VSAM or sequential file, we can push it all the way to the Hadoop cluster in one operation. It's only one step. So how we do that? We wrote a staging server, which is on the right with a purple outline. And we have a library that's called FileUtil. And I'm going to detail both of those components on the next slide. But basically what we do is on the fly compression, we convert the VSAM or sequential files into Hadoop sequence files. So we retain the notion of records, be they fixed or variable length records. And we keep the original charset. So why do we do that? Because we want to be able to make mistakes on what we thought was the charset of the data. Okay? So if someone says, well, my data is using CP1137 and it's not CP1137, then if you've transferred your data and converted it thinking that was the right charset, then what you have on the Hadoop cluster is just junk because it was incorrectly converted. So what we do is we don't touch the charset, we just take the raw data as it was on the mainframe and put it on Hadoop, and we'll handle the charset things at load time when we actually analyze the data. So the staging server. Staging server is really our gateway in and out of an HDFS cell. So it reads and writes to special directories. So it writes to HDFS staging in and whatever path is under that. And it reads data from HDFS staging out and whatever path is under that. It runs as the HDFS user, so it's basically the super user on the cell. And it has a very simple interface that's HTTP based. So basically you post to the staging server if you want to push data to the HDFS cell, and you get to the server if you want to retrieve data from the cell. So when you do an upload, what you have to know is simply the URL of the staging server. So you can multiply those staging server and scale them horizontally if you need to. There are absolutely no limit. The staging server will store directly in HDFS with no intermediary storage. So you can actually stage terabytes of data into HDFS, and it will handle that very happily even with 64 megs of RAM on the JVM. It supports multiple files upload. If you don't specify a target after the /put in the URL, it will create a random directory for you, and it will put the files into that directory, and it will output, after the transfer is done, the list of URLs where your files are actually located. And when you're transferring a file, you can actually, as the staging server is running as HDFS, you can set a certain number of parameters, mainly user, group, permission, or a suffix. So you can decide that you're pushing some data onto the HDFS cell and you want it to be owned by user foo and in group bar, because you have processes after that that are going to move that data, and those processes that move or analyze that data are run by this user or this group. So you can set that at upload time, and same thing for permission or a suffix. You can add a suffix to the data, which is very easy, very handy for generational data sets. The download is the other way around. If you want data to be available to the staging server for download, then you have to move your data on the HDFS cell to a target directory that's under HDFS staging out, and that will automatically assign a URL to the file, so you can actually retrieve the file from the staging server. There's a special feature for sequence files where you can actually ask the staging server to unpack the records, and you're going to get, as a result of that, not the original sequence file records, but you're going to get a text file with, on each line you will have the key and the value, which are going to be either hex encoded or base 64 encoded. Now the file util library, we see it as the Swiss Army knife for sequence file, HDFS staging server, and Zookeeper. It's written in Java, it's a single jar, it works on all our environments, be they Windows, Unix, ZOS, you name them, as long as you have a JVM, then you can run the file util jar. You can run it using a Tivoli workload scheduler or OPC, so you can actually schedule jobs that use that. So you can automate your file upload, your data upload to the HDFS cell using a JCL. You can schedule it using $universe on Unix or cron or whatever. That library has lots of commands. I detailed a few here. The SF stage command will take a data set on the mainframe and convert it to a sequence file on an HDFS cell and push it via the staging server. The stream and file stage command will push a stream or file to the staging server. Not necessarily a data set, ZOS data set, but regular files. File SF stage will take a file and convert it to a sequence file with 1 record per block. So you basically say, my file has 1K blocks, and what it's going to do is that it's going to create a sequence file with a bytes writable value, and each value will have 1K worth of data from the original file. SF archive is like a tar, where you can take lots of different files and actually create a sequence file with 1 file per record. SF pack is used jointly with the unpack feature of the staging server, so you can generate data with key value that's X or base 64 encoded on a text line, fit that to the file util library, and it will create a sequence file on the HDFS cell. For interacting with Zookeeper, we have bedk, ls, lsr, cat, stat commands, so you can easily check if you have Z nodes that are there. And finally, there's a get command, which you can use to retrieve data using a URI. Okay, so that's for moving data. Now, accessing data. First thing we did is think of a way to organize the data so people would easily adopt the Hadoop cluster. So how did we do that? Well, people have been working on the mainframe with a data organization for the last 30 years. So they're used to that. You know, when they see that file, they know exactly what it is. They can tell you that this is retail banking and this is that file and it has this purpose. So what we took is, we took the name of those data sets and we tried to retain the same organization of the data. So all the data coming from the mainframe sits under HDFS data SI, and then we take those little pieces of the original data set name and we created directories so people would actually find the data where they expect them to find. We handle group ACLs at the environment, silo, and application levels. We use suffix for generation data groups, and we follow similar rules for DB2 table unloads. So if you know the schema name and the table name, then you're going to find, if the file was uploaded to HDFS, then the people needing the file will actually find the file in the right place. To access the data, we don't run an open policy for the Hadoop cell, so you cannot connect to the cell from any machine. You have to go through what we call Bayesian hosts. So they're basically controlled machines from which you can actually submit jobs to the cell, but they are the only machine that can do that. So the cells are isolated and all accesses to the cell must be done through those few machines. Anybody connecting to those machines will do so using an SSH key. They will log in with their username. There are no generic usernames to log into the Bastion host. They cannot do SSH port forwarding, so they cannot, open a backdoor to the cell. All shell commands that people actually run on those machines are logged and analyzed if we need to. And the batches, I said earlier that batches could be run from TWS or Dollar Universe. They are scheduled on those machines too. Bastion host can interact with their HDFS cell, so you can basically run any Hadoop FS command. And you can launch jobs from those machines. For all admin tasks, which is creating users or whatever, you need to connect to the name node. So you cannot do that from the Bastion host. So even if the Bastion host is compromised, then you cannot have new users that are created. We're not using Herberts security yet. We'll see if we go through that or not. Working with data. We're a piggy bank. We're a piggy bank. We love pig. We love pig because it's very simple. If lots of people like SQL. Well, they tend to like SQL, but do they really understand SQL? That's the real question you should ask. And the answer is probably no. They just feel comfortable because they know select, insert, delete, whatever. So what we like in pig is the one relation per line approach, and the fact that if you have a data flow view of the analysis you want to do on your data, then this is going to be very easily mapped onto a pig script. Because basically if you do a data flow analysis, you're going to have all those boxes that are connected, and for each box you're going to have one line in your pig script, and that's it. So very easy. So the two boxes that you see here, they translate to a two-line pig script. Other thing we like about pig is that we have no metadata service to maintain. This is not really a big deal for us because most of the data is COBOL records that conform to a COBOL copybook, so we already have that mapping somewhere. So it's not a service, but we have the mapping somewhere, and people are used to that. They know that when they have to read some data, they need to know the copybook. And we have the ability to add user-defined functions. And we have a whole lot of function already in pig, but we did an extension so we can add a lot more very easily. It can be batch scheduled, and it can handle all the data we store in HDFS. That's our main choice, pig, but we're still open to any other tool, so we're not closing the door. If people say, well, I have that very specific use case and I need that tool to actually handle it, then we're open. So how do we load data from all those sequence files into pig? Well, we wrote custom load function that's called a sequence file load func. That's the generic load function for loading or bytes writable based sequence files. Basically what it does is that it will read the raw bytes from the sequence file, and it will rely on helper classes to actually interpret that data at load time. So when you load data into pig, you will say load blah 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 using sequence file load func, and you will specify the helper class and all the parameters for the helper class. The good thing about those helper classes is that they can also be used in regular MapReduce jobs, and they could also be used in Hive UDFs. They're basically taking a row byte array and converting that into meaningful fields. So the schema that the sequence file load function actually outputs to pig is the following. It's a bag that has three, no, it's not a bag actually, it's a tuple of three values. Key, which is a byte array, which is the original key we had in the sequence file. We have value, which is the original value in the sequence file. And we have parsed, which is a tuple, which is the result of the interpretation by the helper class of the raw data that's in the value. So we have helper classes for COBOL. So basically what you specify is COBOL binary helper, and you just give the name of the copybook, and it will interpret the data conforming to the copybook. We have the same thing for thrift. It takes a dot class that was compiled from the generated Java code, and it will generate fields according to that. And for DB2 and MySQL and others, you take the DDL, the data definition statement, so basically the create table, blah, 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 and it will create all the fields with the right types. So what's the initial target for Pig? Well, we have quite a few SAS scripts in the company, and that's our initial target. It's taking those scripts and telling people that they've been running those scripts on sample of their data for a long time. But now they can take the same scripts or the same functional analysis of the data, and they can run it on the whole population. They can run it on the full data, and it will not take any longer than it actually takes today on the sample. So to do that, you need to give people tools so they can reproduce what they did in their scripts. So I don't know if you're familiar with SAS, but usually what you do is you have a data section where you say, well, this is the way my data is organized, and then you say, this is what I'm going to do with the data. And when you define what you're going to do with the data, you have all those nice functions inside of SAS that you can use. So what we need is to make sure that in Pig they can find the same functions. Okay, so if you want to take a substring of something, then we need to provide the same function in Pig. Otherwise people will not be able to convert their scripts from SAS to Pig. So to do that, we're using Groovy. And what we've done is that we created a generic Groovy closure Pig user-defined function. And that Groovy closure Pig UDF can be used in two ways. You can have an inline way of using it. So that's the first define you can see here, where you're going to specify the output schema and the code you want the UDF to execute. And you can have another way to define UDF in Groovy, which will rely on an external file. So that's for UDFs are a little bit more complex than simple substring or addition or whatever. So the schema uses the standard Pig schema syntax. So if your Groovy closure will output a string, then you'll say str colon char array, and Pig will pick that up as a string, as a char array type, when it will generate the tuples. Code, if you input it directly as an inline UDF, is normally a short Groovy closure, but you can have long ones, but then your scripts are just like SQL scripts, you can't read them. And if you're using an outside file, then you need to register the file with a register statement in your Pig script. So you register either a jar or directly the closure.groovy script, which will be available to the Pig script on the cluster. So if you're relying on an outside Groovy file for your UDF, then this is basically the way we lay them down. So we have global import statements, we have constant definition, we have the actual closure definition, and then we have unit tests. And we include the unit test in the Groovy file. So if you modify your closure and you forget to modify the test, then at runtime Pig will actually fail because the unit test will fail. So this is the way it's actually loaded. If the unit tests pass, then the last statement of the Groovy file is return closure. So this will return the closure to Pig so you can actually wrap it into the Groovy UDF wrapper. For type conversions between Groovy and Pig, we have the following that's set up. So you don't have to worry in your Groovy closure about Pig types. You don't have to know about tuples. You don't have to know about bags. It's all converted prior to the call of your closure. So if you have a bag, that's going to end up being a list, a Java util list in your Groovy file. If you have a tuple, it's going to be an array of objects. So you still have to know what objects are in the tuple. If it's a map, it's going to be a map, and the numeric types are pretty straightforward, as are the string and the byte arrays. And same thing the other way around. Your Groovy closure is going to return a standard Groovy or Java type, and this is going to be converted to a Pig type on the fly prior to returning the result to Pig. Wrap up. So for us, Hadoop and the mainframe been working pretty well. We have a fast and rich data pipeline between ZOS and Hadoop, so we can do pretty much everything, move the data in and out of both environments. We have a pig tool, but we built a pig toolbox to analyze COBOL and DB2 data alongside Thrift, MySQL, or whatever. So this opens new horizons for people analyzing the data, because they can actually take the transactions that are stored on the mainframe and analyze that jointly with the web logs, which is something they just couldn't do on the mainframe prior to that. We have the Groovy closure support for rapid extension, so we can build about anything, any user-defined function pretty easily. Very easy to prototype because it's just a file, so you just store the file and run your pig script, and you have the new version that's picked up. But we still have some missing features. So I said earlier that we were using the default codec. That's mainly because we don't want to cope with writing JNI on ZOS. So LZO is out of the picture for us. So maybe we should try out Snappy because it has a pure Java implementation. But we really don't want to do, some Java to C bridge on the mainframe. So you can probably not even hire somebody who want to do that. We would need support in Pig for big integer and big decimal, because when you're working with a sample of the data, it's really no big deal. But when you start adding up all those transactions over long periods of time, then 2 to the power of 45 might not be enough for a double. So you might start losing precision on the summations you do, on the actual numerical computation that you're doing with the data. And we would like some SSH or RSA based authentication tokens instead of Herberts, but we're still debating that. So, and lastly, we have a hard challenge, which is the cultural change. Why is that? Because we're dealing with very nice people who have been working with the mainframe for the last 30 years. And for some of them, the mainframe is God. So you tell them that, your machine might be big, might be black, might be powerful. Well, it was powerful, but we have something that's way more powerful. It's just that, it's a different paradigm, so you're going to have to learn new tools. So at first, they're kind of saying, well, no, I don't want to learn new tools. I like my tools and I can do about anything. Say, well, okay. We're going to show you what you can do with those tools. So usually what we do is that we take a batch or a job that they're running on a periodical basis, something they run, for example, every week or every month. And we tell them, okay, let's take your most complex batch. We'll say, oh, I have this batch that's very complex. It takes 5 hours to run. Okay, bring it on. So look at the batch, write a pig script. I say, okay, I'm going to launch it now. No, you can't launch it now. You can't do that. It takes 5 hours. So okay, I'm launching it now. So we launch it, and usually you chit chat about what's going on and say, okay, that's the result. Can't be done, and that's pretty common. We've had lots of examples where you have people who were running jobs on the mainframe taking 5 to 6 to 7 hours, and you take that time down to 1 minute and 30 seconds. And they're like, wow, maybe I'm going to learn that stuff. So we have easy victories like that, but still, it's hard to make people change their mindset. So, but there's hope, So if you're starting the same thing in your organization, then don't despair. There's hope, and people usually pick that up quite fast when they see the benefit they can actually get from that. Okay, so that's it for me. You can reach me on Twitter. That's our website. Well, it's all in French, so if you speak French, well, you're welcome to visit it, but we don't have an English version yet. Ping me on Twitter if you have questions, and I can take questions in the audience right now. The question was, are we releasing FileUtil to the open source? I'm afraid the answer to that is, for the moment, no. We plan to release to the open source community the Groovy UDF stuff. So that's one thing, because we think Pig could actually benefit from that. probably the Thrift Part 2, not the COBOL one, but we'd be happy to work with you if you really need to. But no, FileUtil it's not on the list of things we're going to open source right now. The question is, are we using the Groovy UDF wrapper to convert the SAS script to pig scripts? We're not doing it automatically, but what we found is that in SAS scripts, you have some functions that are provided by SAS that are not available in pig natively. So we have two ways of going. Either you write pure Java UDF for pig, and you provide that in the environment, or you make a wrapper and you tell people, well, that function that you're using in SAS, one example is we have lots of records that come from the payment system, and then we have to extract substrings. So what we do in SAS is that, what I do, but what they do in their SAS scripts is that they take all those subtokens from the string and they generate new columns in SAS. And then they're going to play with those columns later on in the scripts. So what we tell them to do using the Java UDF is, instead of actually doing several UDFs that will extract several things, just do one wrapper that will handle the whole record. And you're going to output a complex schema in pig. And you're going to say, well, those 5 fields are extracted by one UDF. And usually it's nicer code-wise because you have that code, and then the person will make nice comments saying, okay, this is the part I extract here because this is that kind of record, and that's the way we're working. So we built the Groovy UDF wrapper as a way to enhance the SAS scripts when you transfer them to pig. So they're supposedly nicer when they're actually in pig.
Did you consider R as an alternative?
The problem with R is that you have to distribute things on the cluster. The nice thing with Groovy is that if you're running pig, then you just register the jars and you're off. You can even choose to have different versions of Groovy running, and that will not be a problem. If you're relying on R, then you have to distribute R and install R on all the nodes in your cluster, and then you can interact with it. So. Okay, the question is, we massage the data using pig. What do we do with the result of those pig scripts? The answer, I don't have a clear answer and a unique answer for that because it depends on the use cases. Some people will just, they just want to have an insight on the data, so they're going to run the pig script and just look at the dump at the end of the pig script. So that's one use case. Some other people are just going to select data from massive volumes and produce another sequence file as output, and that's why the generic load function has the original key and value, so we can reproduce a sequence file with a subset of the original key and value. So you're going to create a sequence file in Hadoop, and then what you can do with that sequence file is either get it back on the mainframe and create another VSAM, smaller one with your selected data, or you can push it down the pipe on another pig script so you can do something else. And a third use case is people who would generate, and we still have to clarify that, but people who would generate tab separated value files that they can actually import in a visualization tool like Tableau or ClickView. And that's pretty easy to do because the staging server has the ability to let you download data from the cell. So what you can do is take your pig script, run it on data coming from the mainframe, push it to the output zone of the staging server, and then on Tableau you can just enter the URL of the data and you will be able to visualize it in Tableau. So lots of different use cases where we have identified those 3. Maybe there are a lot more we don't know yet. The more people will adopt that, the more we'll see examples of things we didn't think to. What we liked about pig was the no SQL stuff. So I said we're open to Hive. So if there are things that we cannot do with pig, and the 2 to the power of 45 limit has not been reached yet, maybe if the business goes better, we will reach it very easily, but it depends on our customers. I'd be glad if we don't use Hive, actually. Because if you look at a pig script, and if you look as a Hive query that does exactly the same thing, there is one difference that will strike you right away. The Pig people tend to comment their code. The Hive people, no. So if you switch people actually maintaining those queries, then you're going to have a hard time actually telling the guy, well, okay, this is the SQL query, understand it. Whereas if you put the guy in front of the pig script, then it will read the pig script and say, okay, I know it works, you know? So I know lots of people are used to SQL, but you know, if we can slow down on that, we'd be the happiest person on earth. Any other questions? Well, thank you very much.